Welcome to Topic 10, Lesson 3. You might be accustomed to my bad jokes when we start off these lessons, so I don't want to disappoint. There's two goldfish in a tank. One says to the other, "You drive, I'll man the gun." Think about it. All right. Today we're going to talk about properties of water, and I'm going to introduce you to Henery's law. So let's get rolling. Water is a very common solvent. It's the most important solvent on Earth, in particular for life. Things that are dissolved in water are in your blood. Your blood's mostly water, and it dissolves things and it moves things around your body. So all life, as we understand it to be, uses water as a solvent. And it's very good that we live on a planet that 2/3 of Earth's surface is water. The liquids we drink are mostly water, and a lot of times people think, well, apple juice is some sort of a compound or molecule or something like that. It's just apple juice, right? It's actually mostly water with sugars and vitamins and minerals and things that are dissolved in that solvent of water. And regardless of what it is you're drinking, it's mostly water. 3/4 of our body is water. And that's what, like I was saying, things are dissolved and they can move around easily in the water as a solution. And most of our mass is mostly that water, allowing the solution to move things around in it. It's an important idea, our concept, to understand that if 3/4 of your body is water, that your mass is mostly due to your water. And so a common tactic that boxers and mixed martial artists and wrestlers will use is they compete against people their own weight. And if they are aware that 3/4 of their body is water, what they'll do is through very regimented techniques, they'll spend a week dehydrating themselves in a special way of doing this. And they can lose a lot of water weight. They do their weigh-in and then they can drink and get that weight back. And some fighters lose 20 to 30 pounds. They weigh in like on a Friday, they might be 20, 30 pounds lighter than when they fight on Saturday, when they rehydrate the next day. It's crazy. Personally, I think that you should weigh in when you enter the ring. So we don't do this because it's not really good for you to dehydrate like that.
I love vocabulary.
So water is a polar molecule, and hopefully you've heard this term before, but polar means that it has an uneven distribution of electron density. The electrons are not evenly distributed around the water molecules. So if we take a look here at the actual structure of water, going down a little bit of memory lane, maybe you could pause the video right now and give it a try. See if you can remember how to draw the Lewis dot structure for water. If you did, or not, let's take a look at how you would actually do it. The Lewis dot structure of water is consistent of 2 hydrogens and 1 oxygen. Each hydrogen has 1 valence electron and the oxygen molecule has 6. And so it will create 2 bonds so that the oxygen now has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8, which is a noble gas configuration. And now the hydrogens have 2, which is a neon configuration, which is also noble gas because each bond counts as 2. Anyways, this is the Lewis dot structure for water. And if we look at a space film model, we can see that there's something unique about the water molecule. Where are the electrons? Where do you think the polarity of water is found? So we know that there's electrons in these bonds, but we can also see that the oxygen has more electrons around it than the hydrogens do. So there's a kind of a polarity here with the water molecule, where this side of the water molecule, the side with the oxygen, is more electronegative, and where the hydrogens are, it's more electropositive. Overall, though, water is not charged. It's not an ion. It's not a cation. It's not an anion. It doesn't have a charge. It just has some side is more negative and the other side is more positive. But overall, there is no charge to water. Because water is got a positive and negative side to it, water molecules like to attract to each other. And when a hydrogen is attracted to an oxygen, remember the oxygen side is negative, the hydrogen side is positive, it creates a weak intermolecular force which is called a hydrogen bond. It's easy to break. It's a different type of bond than the connection between the hydrogens and the oxygens. These are covalent bonds that are connecting the hydrogen and oxygen. Their association for water molecules to each other is through hydrogen bonding. This is not a very strong bond. If you think about it, can you stand on water? No, because these hydrogen bonds will easily separate and you'll fall through. However, if you jump into the pool and belly flop, you will still sink. You'll break those hydrogen bonds, but it will hurt quite a bit. So there is a considerable amount of strength here. It's not that it doesn't exist, okay? And this is why water molecules stay in a liquid state under our normal temperature and atmospheric pressure conditions because of this attraction right here. If you get it really hot, the molecules move real quick and they don't have enough time to be near each other to associate, and then the water molecules will break off into a form of steam. Anyways, hydrogen bonds. So if we were to take a balloon and rub it on your hair, you'll create a positive charge on that balloon. And here I've got some students that are testing the charge of their balloon on another student's hair, and the hair is sticking to the balloon, and hopefully you've done that sometime in your life. It's pretty fun. So if you take this charged balloon and you place it near running water, what do you think would happen? If I put a charged balloon near water, now I wouldn't turn the sink on full blast, but just do a nice little run of water like this. And if you put a balloon near it, the balloon is positively charged. And what will happen is as the water molecules are falling down, because the balloon is positively charged, the negative side of the water molecules, which is the oxygen, will associate towards that balloon and be attracted towards the balloon, which I guess, I don't know, if wherever the balloon is, the water molecules are falling, and then they get attracted to that positively charged balloon, and then they start moving towards the balloon, and then they keep falling. So what you see here is water molecules falling. We don't see the water molecules, but water, as they fall, the oxygen side turns, and they will turn and try to go towards that positively charged balloon, and then they'll keep falling. So if you take a balloon and move it towards the water will bend towards the balloon, and when you go like this, it'll bend back and forth, which is pretty cool. It's easy to do at home if you have a balloon. Charge it up on your hair and give it a try. Because water is charged, what happens is if you put things that are charged or polar, just like water is, into water, like sodium chloride, what the water molecules will do is they associate around these charged particles. And in the case of sodium chloride, water molecules get in between the sodium chloride, because we had a solid situation coming out of the the salt shaker, and the water molecules associate around the sodium and chloride. The sodium chloride exists, even though when you put it in the water it seems to disappear. It still exists. The oxygen side of the water molecules will associate near the sodium, the cation, and the hydrogen side of the water molecules will associate near the anion. And they'll absorb, and those ions are going to be floating around in the solution. And this is what's happening in your blood. When you absorb things into your bloodstream that are polar, your blood can carry it around your body and deliver these things, just like what we're having over here. If you keep adding salt, more water molecules will associate with it. But if you add too much and there's not enough water molecules to associate around it, then the salt crystals will just fall to the bottom. That would be a saturated solution. The water can't hold any more of the salt because they're all being occupied with the sodium and chloride. Temperature is a factor of how much how much solute can be dissolved into a solution. As the temperature increases, you can dissolve more things in the solution. And what's happening is the water molecules are being able to move quicker and associate and wrap around these different charged things. It's a little bit easier because they're moving faster to dissolve more things in the solution, if you want to think about it like that. But not everything is equal here. I've got a graph here of 3 different salts. And if we look here, potassium chloride is in the blue. And as you increase the temperature, so this is 0 to 100 degrees temperature, as you increase the temperature, the solubility increases. This is how many grams per 100 grams of water. So you can see that over here, potassium chloride, we're getting more and more and more potassium chloride being able to dissolve in the water as we increase the temperature. But what I want you to note is it's not always the same kind of relationship. Sodium chloride, which is this pink line, pink, purple, whatever, it also increases, but it's not as sharp of an angle or a slope as it is with the potassium chloride. And I included cesium sulfate because cesium sulfate is actually a curve. It's not a linear kind of situation. So this is not a simple formula that we can use for everything. This is separate and different for every different substance. So I just wanted to show you that graph so to understand that. Couple things. One, that the solubility does increase with temperature, but two, it's unique to every different solute. So looking at this graph, just a quick question. What is the solubility of potassium chloride at 40 degrees Celsius? So just practice reading graphs and charts here. At 40 degrees Celsius, but the potassium chloride would be right about there. And I estimate it to be about 30 grams per 100 grams of water. 30 or 39 grams per 100 grams of water would be our solubility. So that's how you would read graphs like this. Another factor that affects solubility is pressure, and in particular, pressure affects the solubility of gases. Yes, water or liquids have gases dissolved in them. The fish breathe oxygen just like we do. Not just like we do, but they breathe oxygen. They metabolize like we do, but they have gills, not lungs, and they are able to extract that oxygen out of the liquid. So if you add more pressure on top of a liquid, you can dissolve more gas into the liquid. I kind of almost picture it like just pressure pushing down on the liquid. It's just jamming more and more of the air into the solution. So, for instance, if you've got a soda can, or which works much better, a bottle, it could be carbonated water or 7-Up or Coke, I guess anything. But if you've got a bottle and you can see in it, there is dissolved gas inside of the container and less gas outside of the container. And what happens is there's an equilibrium where at the surface some of the gas is coming into the container, but at the same rate they're going back. So it's an equilibrium. It's whatever for the amount of gas that's leaving, same amount is going. And there's a lot of gas in here because the container is in a lot of pressure. But when you open up the container, it relieves the pressure and a lot of the gas leaves, and you start to see these bubbles forming constantly in your soda or soda water, constantly forming as the gas is, because there's less pressure up here, there's going to be less solubility in here. So with less pressure, less solubility, and these bubbles will start to go out. It's not an instant situation, it's a slow process. Students have been asking when I talk about this, so why is it when you shake up a can, they explode? Why is there so much more pressure? Why is there so much more water in there? Well, if you take a look at the surface here, the exchange between the gas is at the surface. So there's only this much area where this exchange is going back and forth. If you shake up the can, you push all this air, you mix it all in there, and there's going to be a whole lot more surface area for the exchange of the gas to go in and out. And what will happen is a lot of that gas in here will absorb into your solution. And so when you open up, there's going to be even more gas absorbed into your solution, and it will explode or release a lot faster. Give enough time, it will reach equilibrium again, but shaking it up will just give more surface area briefly, put more gas into the solution, which will make it more violent when you open it. But if you let it sit, it won't blow up on you. Okay. Henery's law. Henery's law is a mathematical explanation that we can make predictions about this solubility of gases. So the decrease in solubility of carbon dioxide contained in the beverage after the cap is removed can be described by Henery's law. Again, you remove it, there's less pressure, the solubility, it starts releasing the gases from there. Henery's law, the solubility, which is represented as a capital S, the solubility of a gas in a liquid is directly proportional to the pressure of the gas in a liquid, and that's a capital P. We represent this as S1 over P1, so the first situation, perhaps the bottle is closed, the solubility over the pressure is equal to the solubility over the pressure in the second situation. So this would be like when you open the bottle. So when you have it closed, you have a high amount of pressure and you have a lot of solubility. When you open it, the pressure decreases, so therefore the solubility will try to decrease, and that's why you get those bubbles. And this is a rearrangement of the equation. Some people like to look at it linear instead of fractions. I like to talk, and you see this in the books and stuff like that, so I'm showing you this way. I like to think about it this way because I think of the first situation equal to the second situation, a direct proportion. Solubility, pressure. If you increase or decrease the pressure, you will directly relate the solubility. So how would we apply Henry's law? Well, you got to get the solubility of something and you got to talk about the pressure. So things like temperature. So look, if 0.85 grams of gas at 4 atmospheres of pressure dissolves in 1 liter of water at 25 degrees Celsius, how much will dissolve in 1 liter of water at 1 atmosphere of pressure at the same temperature? We're always going to talk about the same temperature when we talk about Henry's law. Otherwise, we're going to put in a lot of other factors into this. So Henry's law is about the pressure changing and the solubility changing. And one thing you have to do is you have to figure out the solubility. The solubility is how much is dissolved in how much volume. And I made it easy here, and maybe I made it too easy, because this should be 0.85 grams divided by 1.0 liters. So it's 0.85 grams per liter. So maybe I shouldn't have just put this as a 1. Maybe it's too easy, but if you're paying attention, hopefully you understand what I'm talking about. So the solubility is how many grams over the volume. And I just made it easy saying it was 1 liter, but it could be anything. Let's pretend this was 2 liters. If it was 2 liters, then it would be 0.85 grams divided by 2 liters. So this number would be half as large. Anyways, in the first situation, there's 4 atmospheres of pressure, and that's our solubility, this mass divided by volume. And then in my second situation, I open it up, and now I still have the same volume, but now I have 1 atmosphere of pressure. So what's the solubility going to do? Logically, if I understand Henry's law, the solubility should decrease, and some of this gas is going to be relieved because there's less pressure. So this is what I know, and what I learned was this here, that the first situation is equal to the second situation. Solubility divided by pressure is equal to the solubility divided by pressure in the new situation. We are solving for the solubility in the second situation, so by cross multiplying, I'm going to bring the second pressure up. So the second solubility will be equal to the first solubility times the second pressure divided by the first pressure. And to figure that out, again, isolate here, cross multiply. Now we solve, let's put in our real values here. Our first solubility is 0.85 grams per liter. Our second pressure is 1 atmosphere, and this is all over 4 atmospheres of pressure. So we're going to take this number, multiply it by this, and divide by 4. And I got 0.21 grams per liter, and I think that you probably going to run it through and agree with me. So that is Henry's law, guys. Let's do some practice problems with this just to get you the idea of questions that I might ask on my tests. Alright guys, so here are the practice questions for working with Henry's law. I got 3 of them here. So please pause the video at this point and do your best to try to solve these 3 questions, and then restart the video and I'm going to go over the solutions to them. So please pause it right now. Don't cheat. Pause it. And you paused it and you worked at it. And let's take a look at what I think you should have come up with. So in the first one here, we are given grams per milliliter. So this is a trick here that might, if you get in this habit, it might save you some frustration when you get to the third question here. So remember, solubility is grams per liter, and this just happened to be 1 liter. But if you take the grams, 0.55 grams per 1 liter, you come up with 0.55 grams per liter. That's your solubility. Your first pressure was 2.2, and then your second solubility is what you're solving for, and your second pressure was 1.2 atmospheres. So basically, you have this solubility at 2.2 atmospheres. It's going to have less pressure, so logically, I'm going to reflect when I get my answer, I would think there would be less solubility here. So that's the setup. Our formula for this is we are going to use the equation that the first solubility divided by the first pressure is equal to the second solubility divided by the second pressure. Since we're solving for the second solubility, we would say that the second solubility is equal to, so I'm just cross multiplying, basically this pressure just cross multiplies and moves up here. So the second solubility is equal to the first solubility, and that, remember that moved up, times the second pressure divided by the first pressure. So I plug in values for this, the actual values for the first solubility times the second pressure divided by the first pressure. Atmospheres cancel. I'm left in grams per milliliter, and with two significant figures, it's 0.30 grams per liter. Remember, leading zeros never count, trailing zeros do count. So in your calculator, you probably got 0.3. You got to add another 0 when you write it on your paper, because two significant figures, you'd put 0.30. So that is number 1. For number 2, things that you learned from the question, again, the first pressure was 5.21. The first solubility, I gave it to you in grams per liter. And so this is 0.32 grams per liter. You didn't have to do anything like in the first one you did. And your second pressure is 0.91 atmospheres. So again, you have a lot of pressure. It's going to become less pressure. So you would imagine that the solubility should be smaller. Okay. Our same equation here, that this is again first solubility over first pressure is equal to the second solubility over the second pressure, and rearranging it to solve for the second pressure, again I cross multiply up here, so it's solubility 1 over pressure 1 times pressure 2 equals solubility 2. Plug these values in here, and I would plug in for real values here. I would put my first solubility times my second pressure divided by my first pressure. Put all these together. Make sure I include my units to see things canceling out. The atmospheres cancel out with each other. I'm in grams per liter will be my answer. And the answer I got was 0.056 grams per liter. Again, two significant figures. Leading zeros don't count. This is 0.056 grams per liter is significantly less than what we originally start with, so that makes sense. All right, our third question, and this is why in the first one I actually went through the hassle of dividing and showing the work there, because for the third one you have grams, you have 0.77 grams dissolved in 2.3 liters. So if you take 0.77 grams divided by 2.3 liters, you have the solubility in the first situation, what happens to be 0.3348. I didn't round here because this isn't my answer yet, so I wanted to kind of leave some extra numbers in here. So 0.3348 grams per liter. That's my first solubility, mass over what it can dissolve in. First pressure was 2.8. And then a solubility is going to move to 1 gram per liter. That's going to dissolve more than this situation here. So the second situation has more pressure than the first. So we're going to add pressure to the solution and put more gas into the solution. So this pressure should be greater than 2.8. It's going to take more pressure to put more gas into the solution. So this time we are solving for the second pressure here. And a lot of students, no matter how much we practice this stuff, make this mistake. We're solving for the second pressure. If you were to simply move this down here, if you were simply to move the second solubility here, you would have solubility 1 equals pressure 1 times solubility 2. A lot of people just go right like this. But that would be what 1 over P2 equals, not what P2 equals, not the second pressure. It would be the inverse of the second pressure. We need to know what this means, what this equals. So you got to get this to be a numerator. Therefore, this has to come up if we're cross multiplying. Then now we got to get everything on this side, the left side, to the right side. And when we do that, we cross multiply. They have to go diagonal. So the solubility 1 is going to go down, and the pressure 1 has to go up. So a lot of things are going to slide around here. This solubility 2 is staying alone, but the pressure 1 is going to join it. solubility 2 is going to be joined by the first pressure, and the first solubility is going to move down to here. Rearranging equations, you got to be comfortable with that. You just got to be comfortable with rearranging equations. And a lot of people, with this one in particular, will get it wrong because, like I said, they'll have 1 over P2. So P2 equals solubility 2 times pressure 1 divided by solubility 1. And when we work this out, plugging it in, my second solubility was 1 gram per liter. That's what I want. That's what I want to know. What's the pressure going to be when I have 1 gram per liter? My first pressure was 2.8 atmospheres, and my first solubility was 0.3348 grams per liter. Again, this is figured out by dividing up here, by dividing my grams dissolved in 2.3 liters. So I do that and calculate it through, and I get 8.4 atmospheres. And that makes sense. 8.4 atmospheres is a lot more than the 1 atmosphere I started with, so it took a lot more pressure to increase the solubility, to add that to the solubility. If there's anything on here that you would like further help on, you have any questions on, please note that and save those questions the next time you see me. I'll talk to you soon. Bye.